So in Biot-Savart's law, okay. Sorry. So in Biot-Savart's law, what we saw is, so if there is a current carrying conductor, if there is a current carrying conductor, like from Oersted experiment, we know that a current carrying conductor produces magnetic field, right? So it's a more than like 150 year old story. So what Biot-Savart gave was like how much is the magnetic field. So if there is a current carrying conductor, so at any point, if we wish to find the intensity or the magnetic magnitude of the magnetic field intensity, how much is that? So that was given by the Biot-Savart's law. Okay. So what did Biot-Savart's law stated was, so if there is a current element, so what they do is, so they divide the entire conductor into infinitesimally current elements, infinitesimally small current elements. So this is of length dl. This is of length dl. It's a very infinitesimally small current element, and from there, the magnetic field is directed in this direction. This is our desired point. Suppose point P at which we wish to. This is the desired point at which we wish to find the intensity of the magnetic field. Because of this current element, what Biot-Savart's law gave us, this dH bar is given by the current element. So here the element is given the length, the current element, the length of the current element is denoted as vector cross. So if this is our R bar, the from the current element to the desired point, so the unit vector along that direction upon 4 pi r square. This is what Biot-Savart's law gave. And if we see the magnitude of this, if we see the magnitude of this, what we get is, this is what I dl sine theta upon 4 pi r square. Okay. So this gives the magnitude of this. And so here what we observe is, so well, the intensity of magnetic field. So what are our conclusion? Very first thing is, there is no medium parameter. If you see, there is no medium parameter like mu naught. Okay, there is no medium parameter. First thing, the magnitude of magnetic field intensity depends on angle theta. Now what is angle theta? It is the angle between the current element direction and the unit vector, or the direction in which we are measuring. Okay, so in one direction there is the current element, and another is the direction in which we are measuring. So that angle between them is the theta. Okay, so it depends on angle theta, and depends on theta. Okay, so this is what Biot-Savart's law gave. Now this is because of a finite or infinitesimally small current element. Now if I need for an entire, because of the entire conductor, so I can extend this law. And I can get, so that you will see in the application of Biot-Savart's law, how to find H due to various like configurations. You'll see, like in case of our in electric field, we saw E due to line charge, E due to surface charge, and E due to volume charge. Similarly, here we'll calculate H. We'll calculate H due to different line configuration. We'll see that. Okay, so yeah, so this was Biot-Savart's law. Okay, now we can move towards the application of Biot-Savart's law. Now we have already defined, like in the previous lecture, So in the previous lecture, what we did was we also saw, I mean, I just introduced you the material. So B bar is what? Mu into H bar, right? We also saw D bar, how D bar is epsilon E bar. And what was epsilon? So epsilon was just okay. Yeah, so we saw this, and we also saw this mu and epsilon and mu, if they are for isotropic medium, okay, and we discussed that what is isotropic in the last lecture. So if they are isotropic medium, they are scalars. They are scalars. Whereas for anisotropic medium, they are tensors. है ना? So they will be different in different directions. So it will be like epsilon xx, epsilon xy, epsilon xz. So in different direction, epsilon will be different. Whereas for isotropic, it will be epsilon 0, 0, 0, epsilon 0, 0, 0, epsilon. So along x, y, and z. So x, y, z, x, y, and z. Okay. So we have seen that in the last lecture. Now, because Biot-Savart's law enable us to get the H, so from H we can get B. Okay. So yeah. So next we can move to, so that was Biot-Savart's law. Okay. Now we will apply. We'll see the applications. We also saw in the last lecture. We also saw how like this. What do you say? E bar was minus negative gradient of the potential. So potential is a scalar. Potential is a scalar, and this is a vector. है ना? So what we do is, for different charge configuration, what we do is we calculate V, because calculating V is easy. Why? Because this is a scalar, right? So scalar addition is easy. So what we do is we calculate V due to different charge configuration for line, surface, and volume charge. And then after we get the net V, we calculate the electric field, net electric field. So that is the use of this this relation. So this relation helps us to get E bar for various charge configurations. Okay. So E bar is negative gradient of V. Okay, so this was like what we did in last lecture. So today we'll start with the application of Biot-Savart's law. Okay, application of Biot-Savart's law. So very first application is, so if there is an infinite long line charge, okay, so it's an infinite long line charge, it goes in this direction. Okay, now suppose this is Z direction, so if there is infinite long line charge and we need to get H, at any point. So how to get? So how to get H at any point for an infinite similarly long conductor? Okay. So for an infinite similarly long conductor, if you see, this is our direction of current. So if I pick any current element, ideal, it's like a, so in electric field, what we do is we consider a charge dq. We consider a small charge dq. So here we, because that is the source of electric field there, the source of electric field there is the charge, and here the source of magnetic field is the current. So that is why we take a infinite similarly small current element. Okay. So here we take an infinite similarly small current element, ideal. Okay. So I take an infinite similarly small current element, and this is in this direction. So the direction of current element is the same as that of the current. Okay. Okay. Then we wish to find H at any general point. So what we do is, suppose if I am interested in finding H at this point. So fine. So what I will do, I will simply connect this. we'll simply connect this. Okay, so this is my R. Okay, now because this length is of infinite similar length, if I connect this end also, if I connect this end also, what will I get? So this, so because this is an infinitesimally small length, okay, and we know this is our theta, this is our theta, so this is R and this is also R. Why? Because this dl is very small length, and we know how this doesn't make any difference from basic geometry, we know that. Okay, now so as the current element is in this direction and R bar is in this direction, so what will be the direction of H bar here? Last time we discussed this, how to find. We use, what do we use? Use the right hand rule, है ना? So from Biot-Savart's law, what does it? How do you find the direction? How do you find the direction? It is ideal bar cross R bar. So it's a cross product. It's a cross product of ideal bar cross R bar. So can someone tell me where will the H be directed? Where will the H be directed?
Out of the plane of paper.
Out of the plane of the paper, yes. Like see, it's like ideal is in this direction and R is in this direction, R cap, okay, and this is the theta. So we are moving like this, moving like this. Huh? So ideal bar is in this direction and R cap is in. So we are moving from ideal bar to R cap. So what we are doing is we are going out of the, so it's like coming out of your screen. So I mean I cannot show it, but then this is the coming out of the screen. So how do we represent that? Is we represent it by a cross. So this is like out of the plane, out of plane. And similarly, if I take a point somewhere here, and if I connect this R here, suppose connect this R here, this is R cap, and I wish to find my H, direction of H here. What will be the direction of H here? So ideal bar is in this direction and R cap is in this direction, and I'm going towards this theta. No, this is not outward, this is inward. This is in plane, inwards. And this will be outward. Why? Because we are going like this. You can see my fingers. So ideal is in top and we are going in the direction of from ideal to R. So this will go into the plane of paper. And when we have ideal like this and we are going towards R, so it will be outward. This will be inward. Okay. This will be outward. And so inward we show it back cross. So cross is for inward into the plane, and dot is for out of the plane. Okay, dot is for out of the plane. Now that was a representation. Now we wish to find H because of an infinite similar law, because of an infinitely long conductor. Okay, so there is an infinitely long conductor and we wish to find H because of that. So what I have done is I have considered a current element. And we wish to find H at this point. So I have connected R. Okay. Now, okay. So we have Biot-Savart's law. Okay, we will apply that. So ideal. Now, okay. So let me go to next page. So if this is our infinitesimally long conductor and this is the point at which I wish to find H, okay, and this is my current element which I am considering. So this is R, okay, and this is also R. Okay, they are straight lines. I'm just showing you like there is no difference, okay, but still, because, and this is the perpendicular distance. And suppose say this is capital R, okay, perpendicular distance. and we know this is theta, this is theta, and this is our current element ideal, and this is the direction of current. This is an infinitely long conductor. Now okay, so what can I say? What will be r in terms of small r, capital R in terms of small r? What will be that? So if I take sine theta, if I take sine theta, what will be that? It will be opposite, which is r upon this is the hypotenuse, because this is perpendicular. So this will be r by r. So therefore capital R will be small r sine theta. See, remember, capital R is the perpendicular distance and small r is the distance vector or position vector from current element to the desired point at which we wish to find the h. Okay, now this is dl. Okay, so if I zoom it, if I zoom this, so if this is my dl, this is my dl. Okay, this is my point. Okay, this is my point. So what will be this? See, if this is theta, let me tell you, this will become what? This angle will become what? This angle will become d theta. What will this become? D theta. Why? Because if this entire thing is theta, because because this is a infinite, this is not zero, right? It's a very infinitesimally small, so it will tend an angle d theta, and this is of length dl. So what will be this? What will be this? This will be, so we know from basic geometry that angle equal to arc upon radius. You all remember this? Angle equal to arc upon radius. So d theta. So if this is my arc, okay, arc upon radius, which is small r. So this is r, this is r. So arc, so this length will be what? R d theta. This length will be what? R into d theta. So I can say that my dl is what? R d theta. My dl is, or not dl exactly, this is dl. So this becomes, if this becomes, you can say, if this is theta, so this becomes dl sine theta. So I can say my dl sine theta is equals to r d theta. Okay, why this becomes dl sine theta? Because this is dl. Okay, this is dl and this is the, okay. So we know from, like, if I zoom this area, suppose this is dl and this is our hypotenuse. No, not hypotenuse. If this is angle theta, okay, and this is perpendicular. So what will be my, and this is what we wish to find, x. Okay, so this is dl, this is dl, and we wish to find x. So what will be x? So sine theta will be x upon dl. Sine theta will be x upon dl. So x will be dl sine theta. Okay. So okay, so what we have got is, we have got this length. We have got this length. Okay, so we'll draw, and I will put everything in a single diagram, okay, so that you all understand. So this is the first application of Biot-Savart's law, where we are finding h due to a infinitely long conductor. Okay. So from exam point of view also, this is important. So this is an infinitely long conductor. Okay. I mean, this is not the direction of current. Current is flowing in this direction, but this is the length. Okay. Don't get confused. So I have taken a current element. So this is my current element dl. Okay. And this is the point, suppose, at which I wish to find h. So what I have done is, I have connected this. I've connected this. This was my d theta, and this is what I have got. This is what I have got it as dl sine theta, which was what? R d theta. Why? Because this was d theta, and so arc. So this is like a arc. So arc is what? Angle into radius. So angle d theta. Why? Because this is d theta. Why? Because this entire thing is, the entire angle is theta. So this small angle will be d theta. So dl sine theta. So this arc dl sine theta is r d theta. And we have got, so if this is the perpendicular distance, So what will be sine theta here? So this is r and this is also r. So we have also got capital R, or we have got what? Sine theta is equals to opposite upon hypotenuse, which is this. So capital R by small r. So that implies capital R is small r sine theta. Okay. So we have got few things. Now we'll apply Biot-Savart's law. So we know why Biot-Savart's law, that what does it gives? So it is what? Ideal sine theta upon 4 pi r square. That gives us the h, or that gives us the dh, and then we can integrate it. So fine. So what we have got? We have got dl sine theta. We have got, and we have got small r in terms of capital R. So what we can write about this? So dh, the magnitude of dh will be what? So it will be I into dl sine theta is r d theta upon 4 pi r square. So I can cut it. So this gives me I d theta upon 4 pi r. So I can, so this is dh, okay? So I can take I by 4 pi constant, and so what is r? Basically small r. If you see, small r is what? Capital R by sine theta. So I can write this as capital R, and sine theta will go up. This is d theta. Now this is dh. And how will I get h? Total h, because of all the current elements. So I can divide this into infinitesimally small current elements. So because of all the current elements, what will be h at this point? So simply I have to integrate it, right? So I is constant, fine, it will go out 4 pi, and r is also constant. Why? Because r is what? It is a perpendicular distance, right, from the point to the conductor. So this is also constant. What remains is I have to integrate this sine theta d theta. I have to integrate this sine theta d theta. Can anyone tell me what can be the maximum value if I take all the current elements? If I take all the current elements, what range will theta follow? Hmm?
0 to 2 pi.
No. See, I am taking a point here. So my current elements are distributed like this, one above the other. It's like a stack. So theta will vary from where? Like if I take current element, if I take a topmost, suppose topmost current element here. So from here
0
somewhere,
to pi.
0 to pi, yes. Theta will go from 0 to pi, yes. Now integrate this, what will get? What will get? We'll get h is equals to I by 4 pi r, where r is the perpendicular distance, capital R. And what is the integral of sine? Minus cos, right? 0 to pi. And if we integrate this, if we put the limits, what will get? We will get I by 4 pi r. So minus of cos pi is minus 1. So minus of minus 1 is plus 1. Minus of minus cos 0 is 1. So this will be 2. 2 by 4, it will get cancelled. So we will get, what we'll get is h is equals to I by, so 2 divided by 4, so it will be 2 pi r. Okay, this is the formula for someone as text. Half pi r. Yeah. I by 2 pi. Very good. So okay, so this is the h, which is for infinitely long conductor. This is the h for, yeah. Okay. So this is the h because of an infinitely long conductor. Okay. So I will give you this derivation in writing. I'm preparing notes. I will share with you all. So I mean, this video is also there, but I will give you in a good writing everything. Okay, so this was first application. We'll move to next. So these formulas are very important. Like from your gate point of view, also it is very important. Like these formulas, h is I by 2 pi r for infinitely long conductor. Now we'll move to another application, which is on like how to, for a curve, if there is a circular loop. Okay, if there is a second application. So that was infinitely long conductor. Now we'll move to circular loop. So current carrying circular loop. Okay. Current carrying circular loop. So if there is a circular loop which carries certain current, okay. So suppose if it is carrying a current, and I pick up a current element ideal somewhere here. Okay. So current element. So this is the direction of current element. Now we know if it carries the current is flowing in a loop, so there will be a magnetic field, right? So there will be magnetic, if it is flowing in this direction, so the magnetic field will be in this direction. And magnetic field will be in this direction. So yeah, we wish to find H. We wish to find H at any point. We wish to find H at any point. How to find? So if I wish to now, but here we limit or we restrict our points of observation to the axis of the circular loop. So this is the axis. This is the axis of the circular loop. This is a current carrying circular loop. Okay, here what we do is we limit. So our point of observation will be any point on the circular loop. Okay. So first point, what I wish to observe is I wish to observe what is the H, what is the value of H at the center of a loop. H at a center of a loop. Okay. And then next thing, what I wish is I wish to find H at any point on the axis. I wish to find H at any point on the axis. And once we know that, then we can solve numericals based on that. So yeah, first we'll start 2A at center. So our point of observation is at center of a current carrying circular loop. Okay. So at the center of a current carrying circular loop. Okay. So fine, we can use this diagram also. So suppose this is my current element. This is my current element, or I can zoom it. I can new one. Okay. So our first point of observation is the center of a circular, current carrying circular loop. So suppose this is my loop. Okay, so this is my loop. Current carrying circular loop. Okay. Now this will produce magnetic field. Suppose if the direction of current is this, so I can make the sense of directions like this. Okay, so these are our direction sense. I can write this as X, Y, and Z. Okay. Okay, so this is a current carrying loop. Now suppose this is the infinite similarly small. So we are talking of infinite similarly small current element. Okay. Now this is the center of a current carrying circular loop, and this is the radius. The radius of the circular loop. This is the capital R, we can say, radius of the circular loop. So there in the previous derivation, we used capital R for the perpendicular distance from the conductor. Here, or else if you see, this is also a radius, but radius of what? So if I draw uh, a magnetic field, okay. So the magnetic field, because the current is in this direction, the magnetic field will be circular, and this becomes the radius of the circle of the magnetic field. Okay. There also it's one in one sense it's radius, but here it is the radius of the circular current carrying circular loop. Okay. Here it is the radius of the current carrying circular loop. Now if I zoom it, suppose if this is the center C and this is the current element we are talking of. Okay, so this becomes like this. So this is also radius, this is also radius, and this is my current element. This is my current element. Okay, so this is our center C. So this is the current element I am talking about. Okay. Okay. Now what I am interested in is I want to find H at this point. I want to find H at C. Find H at C. Okay. So yeah, can someone tell me using, like if I use because this is I can use cylindrical coordinate. Like in the last derivation also we used cylindrical coordinates, right? So we used I mean this theta is not in terms of spherical coordinate, don't get confused. Theta here is the angle which the current element makes with the point of observation. Okay, it's not the like the way that we use theta in spherical coordinate system. Okay. Okay, so so if, suppose if I use cylindrical coordinate system here, so this becomes also, if in this direction if I measure, like if I measure my phi in this direction, and suppose, yeah, so if I measure phi in this direction, so this becomes my small d phi. This becomes small d phi. So what will be this? So this length or the arc length, I can say, like see, if you see this is the circle, I mean in which the current is flowing. So direction of current element is this. Ideal bar is this, right? The direction of current element is this, and it's like this. So this is the direction of current element. Okay. And if we wish to find at the center, so our R bar is in this direction, right? So our R bar is in this direction. So what we can say, what is the angle between ideal bar and R cap as per Biot-Savart's law? So ideal bar is a vector, DL bar is a vector, okay, ideal bar is a vector, and R cap, the direction in which we wish to find the H. So what will be angle between ideal bar here and R bar? They are perpendicular, right? So this is like a radial vector and this is a tangential vector, right? So the angle between ideal bar and R bar is what? 90, right? Theta is 90. This is theta between ideal bar and R cap. So theta is 90, right? Is this fine? Is the diagram not clear to you all? What is it flying? Sohan? Is the diagram not clear, or I mean?
Sir, can we just draw it?
Huh?
It's a bit
Confusing. Okay, okay. I will again, because this is second application. There are numeric. I mean, in exams, numerical comes based on this. So let me make it, or I will go to new page. Okay. So suppose there is a current carrying circular loop. This is in a horizontal plane. Okay. I mean, this is in a horizontal plane, and so this is a current carrying circular loop. Current is flowing, and suppose if I orient this, suppose this is the center. So this becomes my x-axis. This becomes my y-axis. Sorry. Okay, fine. If I write this as x, y, and z. Okay. Fine. Now, what I wish is, so this is a current carrying circular loop. I wish to find H because of this current carrying circular loop at the center of this loop. Is the objective clear?
Yes.
Okay. So we wish to find H at this point. Okay, so what we'll do, we'll take some finite current, infinitesimally small current element, right? That is how we follow. We take an infinitesimally small current element and we get the magnitude of h because of that infinitesimally current element, and then we integrate, right? So how will we integrate? We will integrate along this length of the loop. We'll integrate along the length of the loop. We'll get the total h because of the current carrying loop at the center at this point. So first we'll find h due to this current element dl, right? है ना? Okay, so that is the procedure we follow, right? Okay, now suppose, what is the direction of dl bar here? What is the direction of dl bar here? So one, what is the direction of dl bar? It will be tangential, right?
Along
At
the
every
tangent.
at every point, if you see, the direction of dl bar will be tangential. Like if you see here this, so at every point it is tangential. So ideal bar is always tangential. Why? Because it's a it gives it a direction, right? So even though current is flowing in a circular loop, but the direction of the ideal bar is always tangential to the circular loop. Okay, and we wish to find at this point, so we'll connect this point, right? We'll connect this point, and so this is, so what about the direction of, this is the direction of r cap, right? So ideal bar and r cap, they are perpendicular, right?
Yes, sir.
So this is my r, है ना? Ideal bar and r are perpendicular, right? है ना? Is it not okay?
Okay, sir.
Ideal bar and r cap, this is our r cap, okay, in this direction. Why? Because our point of interest is here. So ideal bar and r cap are perpendicular. So our theta, which is angle between ideal bar and r cap, okay. Why? Because we are taking cross product, right? We are taking cross product. So our theta, what is theta here? Theta is 90, and we know sine 90 is 1. So this becomes ideal. This becomes ideal. Ideal sine theta, but sine 90 is 1. So ideal. Okay. Okay, fine. So what we get is, we get dh at this point C is what? Ideal sine theta, which is what? I into dl sine theta is ideal upon 4 pi, and r is what? Capital R square, right? Is this fine?
Yes, sir.
Okay. Now, but this dh is due to this current element, small current element, infinitesimally small current element, right? So what we do? We integrate this. We integrate this over the length of the loop. We integrate this over the length of the loop. So this is like a closed line integral. So this sign, what does it mean? It means
Closed loop.
closed line integral. Closed line integral or closed loop integral. Okay. So we are integrating along a closed line. So when we integrate this, what do we get? So I is constant, fine. 4 pi r square is constant, and the integral of dl, what will it give? It will give 2 pi r. So r I can cut, 2 pi I can cut, so it will be 2, so it will be I by 2 r. So this is the h at the center of a current carrying circular loop. So this is the h at the center of a current carrying circular loop. Fine. So this was our second application's first part, at the center. Any doubt in this?
No, sir.
Okay. Next we can go for same thing, same diagram. Okay, same diagram. So this is a circular loop, and there is a current element, and this is our diagram x. This is our directions x, y, and z. Now what I wish is, I wish to find at a point on the axis of this loop. So if this is the loop in which current is flowing, so this is the axis. So z axis is what? Axis of the loop. Z-axis is what? It is the axis of the, right? So we have found H at the center. Now I wish to find H at any point on the axis. 2B. I can say this is 2B at any point on axis of the loop. So suppose this is point P. So here I wish to find the H. Here I wish to find H. Yeah. So my current element is here. My current element is here. So this is my DL bar. Okay. And so from here, what I will do, I will connect this point, right? Sorry. So from here, so this is my current element. From here, I will connect. This will give me R cap. This will give me R bar or R cap, right? So this will give me R, है ना? This will give me R. Okay, is it fine?
Yes.
Till here, is everything okay?
Yes, sir.
Students, other students can also reply.
Yes, sir.
Yeah. Fine. So yeah, so the current element is here. So this is our current element, and this is the point of interest at which we wish to find H. We wish to find H. And we have seen once we know H, we can find B. Once we know H, we can find B. B is mu H. And once we know B, there are many other things that we can calculate the flux. So they are all related. Okay. So, so this is R. So we have got R, small r. And this is what we have already seen. This is what? Capital R. This is a capital R. So if you see this triangle, if you see, suppose if this is point O and this is point A, triangle OAP. Can you all see triangle OAP? Okay? Yeah. Yes. So from this triangle, what we'll do is, so I can write this point P is at a distance Z from the origin. Point P is at a distance Z from the origin. So what relation I will get from here? From here, what relation I will get? I will get R square is equals to capital R square plus Z square. Okay? By Pythagoras, I will get this. So from here, I will get R, which is what? Under root R square plus Z square. So R is the radius of the loop, capital R. This is what? Radius of the loop. This is the distance at, or this is the point. I mean, this is the distance from the origin. Z is the distance from the origin, the distance of the point at which we used to find H from the origin. Okay. So this all things, this all data they give in the numerical. They will give you the radius of the loop. They will give you the distance at which you wish to find. You are supposed to find the H. Okay. So you will get small r. Okay. Now once you get small r, so can someone tell me? So if DL is in this direction, if DL is in this direction, and R cap is in this direction, where will be the direction of DH? It's like DL, DL, and R cap. Or if you can see this, so DL is in this direction and R cap is in this direction. So where is my thumb pointing? So it's like, see, I will make here. So DL is in this direction and R cap is in this direction. So where will be the, yeah, someone has written along OP. No, not along OP. Not along OP. So if DL is in this direction, so it's in horizontal direction and R cap is in this direction. So the resultant vector will be perpendicular to both, and it will be along this direction. It will be along this direction. DH. It will be along this direction. Okay. It's like, what do you say? So DL, I mean, maybe see, I will make it again. So our loop is this. Okay, so dl is in this direction, and there is a point somewhere here. Okay, and this is the direction of r cap. So they are perpendicular. Okay, r cap and dl are perpendicular. Can you all see that? R cap and dl, they are perpendicular, right? So when I go from ideal cross r, ideal cross r, ideal cross r, if you see my fingers, ideal is in this direction, ideal is in this direction, and I'm going towards r. So where is my thumb pointing? So my thumb is pointing in this direction. So ideal cross r. So my thumb is pointing in this direction somewhere, right? So dh is in this direction. Is it okay? Is the sense of direction clear? Hmm?
Yes, sir.
Not clear?
Clear.
Okay. So now we wish to find dh, right? We wish to find dh. So the direction is in this direction. What is the magnitude? Okay. Let us first find the magnitude. So we know dh from Biot-Savart's law. It is what I dl sine theta upon 4 pi r square. Now what will be theta in this direction? So we know r cap and ideal, they are what? Perpendicular, right? They are perpendicular. So theta becomes what do you say, 90. So sine 90 is 1. It's gone. So it will be ideal upon 4 pi r square. But what is r? What is r? We have already obtained what is r. So this will be r capital R square plus z square. Is this fine, students? Still here? This is the magnitude of dh, and this is the direction of dh. Is it okay? I mean, reply so that I get to know like whether. Is it tough? I mean, do you all find this tough? Okay. No. Okay. Sohan is only Sohan is replying. No one is replying. I mean, are others sleeping or what? So it's Friday, holiday morning. Vedant,
Yes, sir. Sir, it's easy, sir.
it's easy, right?
Yes, sir. It's we have studied in 12th.
Yeah, that's what. That's what I am. I mean, these all things you have studied in 12. But only thing is here we give some significance and we represent it in a different way. So physics remains same. Only thing is we in engineering we represent it in a different way. That is the difference. Okay. So these all things are there in our JW syllabus also, but then we represent it in a different fashion, and we study significance in detail. That we'll see when we'll come to Maxwell equations. We'll see the significance of all these things. Okay. 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 Now this is dh, but what I want is I want along the axis. I want h along axis. Okay. That means I want the z component of h. I want the z component of h. So this is h dh. Okay. This is dh. Now what I wish is I get dhz. So in this direction, what will that will be? It will be dhz. So see, if this angle is alpha, suppose if this angle is alpha, okay. So what will be cos alpha? So cos alpha will be what? Adjacent upon hypotenuse, which will be capital R by small r, right? है ना? Capital R by small r. Okay. And so if this is alpha, so this becomes 90 minus alpha, and this is 90. So this also becomes alpha. Okay, this also becomes alpha. So from here, what will I get? I will get cos alpha. I will get cos alpha is what? It will be adjacent, which is dhz, the z component of hz upon dh. Or that implies I will get dhz is equals to cos alpha into dh. So I have got dh, I have got dh. What I need is I have to simply multiply with cos alpha. I have to simply multiply this with cos alpha. I will get dh z or the z component of. So if I multiply, what will I get? So that means my dhz will be what? I dl cos alpha upon 4 pi r square plus z square raised plus square z square. Yeah. Now, but what is cos alpha? It is capital R by small r, right? Capital R by small r. But what is small r? Small r is what? Under root r square plus z square. Under root r square plus z square. So this will be I dl. Okay. Cos alpha. Cos alpha is what? Capital R divided by r square plus z square ka root, and there is a term here. So this term into root of this term. So this will become what? R square plus z square raised to 3 by 2. Why? Because this is power 1. R square plus z square raised to 1 and r square plus z square raised to half. So 1 plus half is 3 by 2. So this is our dhz. Yeah. Any doubts? Okay. So this is the dhz we have got. Now we need to get total h. I mean total hz, total magnetic field intensity along z axis or along the axis of the circular loop because of the entire loop. So this is because of this current element ideal. This is because of the current element ideal. So what I've got is I have got dhz as what? I dl into capital R upon 4 pi r square plus z square raised to 3 by, right? Ideal R upon 4 pi r square raised to 3 by. Now what? How will I integrate this? So if I integrate this, how should I integrate this? Can someone tell me? Hmm? So my length, if you see my length, I will integrate it along length, right? Anna? Line integral. So what I will get? I will get I. What will I get? DL is what? IR upon 4 pi r square plus z square raised to 3 by 2 into 2 pi r, right? Integral DL is 2 pi. So 4 pi, 2 pi gone, 2 remains. So what will I get? So my hz, or this is what? H along the axis of a current carrying circular loop. Okay. So hz, what I will get? I will get it as I r square upon 2 r square plus z square raised to 3 by 2. That means if there is a circular current carrying loop, okay, so at the center I have got h, and the axis, and at any point on the axis I can get. So this is at any point on the axis. This is what? H along the axis. H at any point, not along. It is at any point on the axis of a current carrying circular loop. Now from this, can I get? So if my z is 0, if I put z is 0, what will I get? So I will get, so h at 0, h at origin, at the center. So this will be what? IR square upon 2 r square, z square is gone, so this will be 3 by 2, so 2 gone, r cube, r square is gone, so I will, what we will get? We will get I by 2. So this is the same as which we derived, right? This is the same thing which we derived here. H is I by 2r. for a at the center of a circular loop, right? So this derivation is a general derivation for a circular loop. So till now what all we saw two things. Today especially we saw the applications of Biot-Savart's law. We started with the infinitely long conductor, okay, infinitely long conductor, and we obtained the h due to h at any point due to infinitely long conductor, which was I by 2 pi r, I by 2 pi r, where r is the perpendicular distance from the conductor, okay. And then we obtained the h due to h at the center of a circular loop, and we obtained the h at the center of circular loop, which is I by 2 r. And then we obtained the h at any point on the axis of a circular loop, which is this ir square upon 2 r square plus z square raised to 3 by 2. And if we put z equal to 0, that means if you wish to find h at origin or at the center of a circular loop. Why origin? Because I have placed it along the axis. So this is my x, this is my y, this is my z. So this becomes the origin. Okay. Or if we are, I mean, at the center of a circular loop. So this is the derivation which you have already derived, I by 2 pi r. Okay. Okay. Now I think I mean, should I solve numericals based on this, or should we move to the next topic? Should we move to the next topic? I mean, next law, Ampere Circuit Law, or should we solve numericals based on this? क्या बात है, सो रहे क्या?
Sir, we will be solving the numericals like today itself or in the next lecture if we like continue with the next concept.
If you continue with?
Sir, if we continue with the next concept right now, sir, when we will be like solving the numericals? In the today's lecture only,
or maybe should I solve one or two at least so that you will get
yes,
to
sir.
know how to, है ना?
Yes, sir.
Yeah, at least we'll solve one or two so that you understand like how to solve. See, simply we have formula, right? So it's not like very tough. So we have formula, which is what h is equals to I by 2 I by what all things should derive, I by 2r for center of a circular loop, है ना, for I by 2r for center of a circular current carrying loop, and h is what I r square. Yeah, someone is saying something. Solve one numerical as examples. Okay, yeah, I will solve one or two numericals, don't worry. Okay, so I by 2r and then ir square by 2 I. So these are just, I mean, numericals will be straightforward formula based, so you don't have to, I mean, use your, only thing is you have to understand how to apply, that's all. And these are for current carrying circular loop at the center at any point along the axis. Now for infinitely long conductor, for infinitely long conductor we obtained h, which was what I by 2 pi r, where r is the perpendicular distance. So let us solve a numerical. Suppose let me take an example. Suppose I will take example on this. Okay. So suppose there is an infinitely long conductor carrying a current of 10 ampere. So there is an infinitely long conductor, okay, carrying a current of 10 ampere, suppose, and I wish to find at what distance my h will be say 1 ampere per meter. So I hope the unit of h is clear. Last time we discussed this in the last lecture, h, the unit of h. So this is ampere per meter, right? So there is a conductor which carries a current of 10 ampere, and I wish to find at what distance h will be 1 ampere per meter. So h is given, I is given, I wish to find r. So you all can do it, right? Fine. Or should we solve this? So what will be r? So it will be I by h into 2 pi. So this will be 10 divided by h is 1 into 2 pi. So this is 6.28 and then 10 divided by 6.28, it will be something 1.5 or 1.5 or 1.6, whatever. Okay, so R will be that much meter. Fine. Okay, now say another example. If I say like if you have been given, suppose so there is a loop, say there is a current carrying loop of say some radius, say 0.5 meter. Okay, there is a loop, current carrying loop of say radius 0.5 meter, and it produces a magnetic field of say 1 ampere. I mean, just I am taking simple numericals so that you understand how to apply. It's producing a magnetic field of say 1 milliampere per meter, 1 milliampere per meter, and we used to find yeah, so we used to find how much current is flowing, in the loop. Okay, how much current is flowing in the loop of radius 0.5 meter. So this is our radius. Okay, so the loop, suppose there is a loop of radius 0.5 meter, and the h is given, h at the center is given as 1 milliampere per meter. So h here is 1 milliampere per meter. And what is the current? So simply we know h is what? I by 2r, right? So I will be what? H into 2r. So that will be h is 1 into 1 milli, which is minus 3, into 2 into r, which is 0.5. So 1, so it will be 1 milliampere, right? So this is how we solve. Now suppose if we wish to find what is the, so there is a loop at a height of say at a height of 2 meter, at a height of 2 meter, what is the h? What is the h? So we know what is h. So it is what? I r square upon 2 r square plus z square, raised to 3 by 2. Can someone help me? So what is I? The current flowing through the conductor is what? If I take the same loop, so it will be 1 milliampere, right? And R is constant, obviously, so 0.5 into 0.5, and say 2 into R square, so 0.5 square is say 0.25 plus z square. So z is what? It is the distance from the axis, so this is our z, right? So this is 2 square, which is 4 raised to 3 by 2. So if you'll solve this, this is 0.5 into 0.5, 0.25, and so this is 4.25 raised to 3 by 2. So I mean, you have to use calculator. So this gives somewhere around 14 micro ampere per meter. So h value gives is 14 microampere per meter. So is this fine? I mean, this is how straight numericals will be straightforward. You don't have to very much. So either it will be at the center or at the along the axis, or it may be because of an infinitely long conductor. So you have to simply apply the formula. So this was Biot-Savart's law. I hope you all have understood the Biot-Savart's law and its application. Yes, Rohan, Aditya, Divyaman, समझा सबको? Okay. So let's move to another topic, which is Ampere Circuit Law. Okay. So where we stopped here is, I mean, we derived. So because of an infinitely long conductor, what was h? It was I by 2 pi r, right? Or if I simply say what is 2 pi r, basically it is what? Or I can say this implies h I is what? H into 2 pi r. But what is 2 pi r? This is what? This is a simple line integral, right? So I can say this as line integral of h bar. I hope you all remember what is divergence theorem and Stokes theorem. Do you all remember? Vinit sir must have introduced in the initial lectures divergence and curl. I think those who are regular students, they may remember divergence and curl. So, should I revise that?
Yes.
Because that will be using in Maxwell's equation also. So diploma students, I think can tell me whether they have, I mean, whether they were there during divergence and curl. I mean, when Windsor was taken. Hmm? Okay, Shreyas says please revise. Fine. Okay, fine. So because we will be using this divergence and curl frequently when we will using Maxwell equation. So let me quickly revise divergence and curl, like for the benefit of all. Okay. So I mean, I will not go into the formulas. Okay, that you will get in any book you pick on electromagnetics. You will get for different Cartesians, for different coordinate systems, for different coordinate systems. You will get all your coefficients, है ना? H1, H2, H3. You will get coefficients, and you will get divergence. Okay, and you will get curl formula, okay, for different coordinate system. So let me first go through the importance or the significance of divergence and curl. Okay. So if A is a vector, if A is a vector, okay, and so you all have studied Gauss law, right? So can anyone tell me Gauss law? Anish, can you tell me what is Gauss law for electric field? Hey, Baba, you all have got more than 20 in your in semester. So at least tell me what is Gauss law. Vignesh, Gauss law for electric field.
Sir, this is Anish.
Yeah.
So it states that the total flux through any closed surface is equal to the charge enclosed.
Total flux through a closed surface. So this is a closed surface. Okay. So it's a closed surface. So just remember the word closed surface. When you say closed surface, what does it mean? It means that it encloses some volume, right? And we say closed surface, that means it encloses some volume, and from that vectors are coming out. Okay, from that vectors are coming out. So in case of electric field, this is d bar or e bar, है ना? So whatever amount of this d bar comes out, whatever amount of this d bar, so I hope you all remember what is d bar, the electric displacement, right? Hmm? You all remember d bar we covered last time. So the electric displacement, whatever is coming out, okay, through a surface S, through a surface S. So it's like d bar is coming out through a surface S. But like, see, so if d bar is in this direction, if I pick a surface here, so surface area is in this direction, my d bar is in this direction. So d bar is in this, surface area is in this direction, right? D bar is in this direction, surface. So there is an angle between d bar and ds bar. So what do? How do we get the total outward quantity? So how do we get the total outward quantity? We take a dot product. We take a dot product of d bar and ds bar, right? Hana? And if we do it along the entire surface, so this is for a particular ds. If so, this is like ds1. Okay, this is d1 into ds1 plus integral d2 into ds2. I hope you all have solved numericals of this kind. I mean, where you add flux through each surface, or है ना? So d1 dot ds1 d2 dot. So if you go on adding for the different surfaces, okay, where there is d bar. So what do? We take a dot product. So that means if the surfaces are continuous, what we can do? We can take integral closed surface integral. So this is called closed surface integral of d bar dot ds bar. Is this okay? You are getting this, what I'm trying to say? Closed surface integral of d bar dot ds. What does it gives? What Anish said, it gives the total charge enclosed. Right? Total charge enclosed. Now this is for a closed surface. This is for a closed surface. So what is divergence theorem? Let me tell you. This is not divergence theorem. This is Gauss law. Okay. This is Gauss law. What is divergence theorem? What does divergence theorem say is that if there is a closed surface, okay, if there is a closed surface, and if there is an outward vector quantity, so if there is an outward vector quantity, so it's like a divergence. So the outward quantity, vector quantity is diverting. Okay. So there is outward flow. So this d bar dot ds bar, this d bar dot ds bar is, as per Gauss law, this is the charge enclosed. Fine. But suppose, okay, if we want to represent it using divergence, so what we can do is, so let V be the volume, let V be the volume of this closed surface. I mean the closed enclosed surface. Okay, let V be the volume, and we know. See, we all deal with charge distributions. Okay, so charges are distributed. Similarly, in magnetic field, the current elements, we deal with current elements. Okay. So it's not like at every point there is an equal charge. No, there is at every point on the conductor there will not be an equal current flowing. Okay, there will not be an equal current flowing. So we'll see when we study current density, our next topic. We'll see that the current flow is not what do you say, uniform. Okay, and that is why we define something called as current density. Similarly, the charge distribution is not uniform. That is why we define something called as charge density, right? You all have studied different charge configuration. So we define something called as charge density. And what is charge density? So if I define volume charge density, it is rho v. You all remember, right? Volume charge density. This is what charge per unit volume, right? So because the charge distribution is not uniform, we define a charge density. So it can be a line charge density, because along the line, the charges may not be uniformly distributed. So we define charge per unit length, that is lambda, charge per unit length, and then we define, there are different symbols in different textbooks. So line charge density, this is called line charge density. Similarly, we define something called as surface charge density, and here we define volume charge density. So volume charge density symbol we use is rho v. Rho. Okay, is this fine till here? I mean, this is Gauss law, where we study the closed surface. Along the closed surface, there is an outward vector, and we use this dot product. So why we use dot product? Why? Because they can be along a different directions. So to get the net outward vector, what we do is we use the dot product. Now, what does divergence theorem says? So we have got total charge enclosed, right? So what will be Q from here? So Q from here will be, so if it is dq, so it will be dq rho v into dv, rho v into dv. But if I want total Q, I will integrate this. So my total Q will be integral of dq, which is what? Volume integral of rho v d. So from here, what we get, this, that is called as divergence theorem. So what have we seen? From Gauss law, we have seen that d bar dot ds bar is q, okay, along a closed surface integral. And similarly, this is also equals to volume integral. Volume integral means we can put three integrals, okay, is rho v into d. Okay. Because it is volume, so we'll integrate along in three directions. Like in case of Cartesian, it is x, y, z. In case of cylindrical, it is r, phi, z. So this dv will become dx, dy, dz. It will become r, dr, d phi, dz. It will become r square sine theta, into dr, d theta, d phi. So these are for different Cartesian system, different coordinate systems. You will get in any book. Okay, how to represent that. So that all things you can get in any, even in local books you will get. Okay. So so this is what is divergence theorem. So what does divergence theorem says? So the surface, the closed surface integral of any vector, okay, the closed surface integral of any vector can be expressed in terms of volume integral. So that means I can express this as volume integral of, okay, I can express this as volume integral of divergence of d bar dot, divergence of d bar d. This is volume integral law. So that means what I get is this is equal and this 2 becomes equal. So I can write this as volume integral of del dot d bar minus rho v into dv equals to 0. Now for any arbitrary volume, for any arbitrary volume, okay, for any arbitrary volume, if this gets satisfied, what we can say from this, we will get something called as del dot d bar is equals to rho. So this is the differential form, because this del is what, I hope you all remember what is del. So in case of this Cartesian system, it is d dou by dou x ax plus dou by dou y ay plus dou by dou z az. So this is a vector. This is a vector operator. This is called del, or the gradient. I mean, when we apply this, so I mean, these all things Vinit sir has taken in detail, hai na? So we don't need to go back. So this is the relation which we get, which is called point form, because this equation. Okay. So this is called integral form. This is called integral form, and this is called point form. Why? Because this is valid only at a particular point. This is valid only at a particular point. So I hope you all have solved numericals based on this, on Gauss law, you know, where you will be given d bar in a particular Cartesian, particular coordinate system, and you need to take divergence. You need to take divergence of that. You need to take divergence of that, and you will get the rho v. And once you get rho v, you know, you can integrate it over a given volume. You will get the total charge enclosed. So that is the Gauss law for electric field. Gauss law for electric field. Have you all solved numericals based on that in your tutorials or somewhere? On Gauss law, Ame, Vignesh, based on this divergence, del dot d bar is equals to rho v, hai na? Must have solved, right? Hello. Vignesh, Ame.
Yes, sir, we have solved.
You have solved numericals, right?
Yes, sir.
Yeah. Okay. Fine. So this was divergence for electric field. Now we'll go to the magnetic field. Okay. We'll go to the magnetic field, and we'll see how this gets applied. Okay. So what we saw in electric field, that d bar dot ds bar over a closed surface was giving us the total charge enclosed, right? Whereas for magnetic field, if you see, for magnetic field, if you see, okay, for magnetic field, if you apply the same law, okay, so that there is, it is electric displacement, and here it will be magnetic field b bar dot ts bar. What you will get is 0. What you will get is 0. Why? Because let me tell you, see, in case of electric field, suppose if this is a enclosed surface and there is some charge q1, q2, q3, q4, hai na, some plus minus, so there will be something, there will be some charge enclosed, okay? With the algebraic addition, you will get some charge. Whereas in case of magnetic field, suppose what is a magnet? So it's like, suppose if I take a magnet, so there is a north pole, there is a south pole. So there will be some outward flux, or there will be some inward flux in case of electric field. In case of electric field, there will be some outward or inward flux, and that will give us the total charge enclosed. Okay. Whereas in case of magnetic field, what we see is, okay, in case of magnetic field, what we see is, so goes from north. Okay, so the flux goes from north to south. So if you enclose this, yeah. So if you enclose this in a closed surface, so what will be the net flux? Can you tell me? So what will be the net flux? whatever is going out, same is coming in, right? Whatever is going out, so here is something is going out, same thing is coming in, right? So if I put a closed surface at any point, if I mean of any volume, is it not okay? Students, are you all getting what I'm trying to say? See what I'm trying to say. In field, audible, students?
Yes.
So, okay. Now is it fine?
Yes, sir.
Okay. Yeah, so what I was trying to say is, so in case of electric field, okay, so if you enclosed us, I mean, if you put a, that is called, what is, we call that as Gaussian surface. Okay, we call that as Gaussian surface. Okay, so if we enclose a particular set of charge, so there will be, because of the positive charge, there will be outward flux. Because of the negative charge, there will be inward flux. Okay, so there will be some net flux. है ना? Or it may be zero if they cancel each other. Okay, but in case of magnetic field, it is always zero. Why? Because see, in case of charges, they are all discrete charges, individual charges, plus q, minus q. Okay, they exist separately, they exist individually. In case of electric field, plus q and minus q exist individually, whereas in case of magnetic field, you cannot have a north pole separate and a south pole separate. You cannot separate them. Okay, so because we cannot separate the north and south pole, so whatever flux is going out, same has to come in. Whatever flux is going out, same has to come in. Whatever flux is going out, same has to come in. Okay, so it's like, so if you put any Gaussian surface, if you put up any Gaussian surface, okay, any Gaussian surface, suppose whatever flux is going out, same is coming in. So the net outward flux will be what? Or the net flux, not outward, sorry. The net flux will be what? Zero, right? Why? Because whatever flux goes out, it same comes in. Why? Because the north and south pole, we cannot separate them. So there is no monopole. There is no monopole exist, because there is no monopole existing. So for magnetic field, this is our Gauss law. Is it okay? So if I integrate over a closed surface, the net magnetic field, if I do the surface integral of the the magnetic field, what I will get is zero. So this is the Gauss law for magnetic field. If I integrate the surface, this is the outward vector, this is the vector b bar. If I do the dot product of b bar dot ds bar, I will get zero. So using divergence theorem, what can I say? I can say this, that if I extend it to volume integral, del dot b bar dv is zero. That means there is no charge, or there is no net magnetic charge. This implies what? No net magnetic charge. So there is no net magnetic charge. Why? Because they cancel, right? They cancel. So what we get is, and because there is no net magnetic charge, so this is like your del dot d bar is rho v dv, but here there is no rho v, there is no net volume charge. So the net magnetic charge is 0. So what we get is del dot B bar. Del dot B bar is 0. Okay. So this is the integral form. This is the integral form of Gauss law for magnetic field. Okay. This is the point form of Gauss law for magnetic field. Okay. So is it okay till here, students? Okay. So let us solve few numericals based on this. So you will understand. You will have a better understanding. Okay. Let us solve one numerical, and then I think we can take a break. Because you all may be tired. So let me solve some numericals. Ampere Circuit Law we have not covered yet. Or let us cover. So this was Gauss. So we'll quickly revise what all things we have done. Okay, we started with H for infinitely long conductor. Okay, then we obtained it for current carrying circular loop, and then we obtained it for along the at the center along the axis, and then we saw Gauss law for magnetic field. Okay, we got the relation del dot B bar is 0. Okay, and we also saw Gauss law for electric field, where we saw del dot D bar is true. Okay, so I hope you all have solved numericals based on this. So that there is no numerical based on this. Why? Because this is 0. And next we can move to what a very important law, or maybe we can take a break of 10 minutes and then we can resume. What do you all wish? What should we do?
Sir, a break for 10 minutes. Sir, we can continue at 11:11.
Okay, fine. Or we can take a break of say 15 minutes if you all want.
Okay, sir.
Yeah, and then we can meet at 11:15, and then I will take. I have to take 2 more laws. I will finish with. I will try to finish Ampere Circuit Law. Okay, this is a very important law, and I will try to finish Faraday's law. Okay, and so this will cover your third module. Okay, this will cover your third module.